drafted market status with tracking applications. In this research, we use a recent implementation of language to modify some designs of open code. Also, code is available for from GitHub, from those you can try to run the program of your browser by clicking the URL. We will demonstrate the tool later in the presentation. Okay. So our research question is how can we extend general purpose programming languages, including functional languages, using the ideas from graph translation. Functional languages support complex data types. However, they can only represent this or these. These are the only data structures that the programming general purpose programming languages for faster to talk about. In our research, we are developing a new functional language as LangCGT, which can handle data structures that are beyond speed, or in other words, graphs, and faster values with faster numbers. For example, a data sheet with our list with additional links to the last node, after link this, increase, and present trees. So here is our first LangCGT program. This program concatenates the differences. Here we have a random structure. Since it is a function, of course we have variables. This time x, but we can clearly see something different from ordinary random factors. We have the notion of pre-links. These are links that can reconnect subgraph to compose larger graph. So, applying this function, we avoid differences from 1 and 2 after a new function. New function because the random structure about and applying this function is differences from 3, but we concatenated differences from 1 to 3. So I want to run this program on our interpreter. So here we have the first differences from 1 to 3. And we also have another difference list on 4 and 5. And we also have a function. And applying these two difference lists to a function outputs a new concatenated difference list once 1, 2, 3, 1, 2, 3, 4, and 5. So now the difference list has concatenated. So far we have shown how LangCGT composes graphs. So now let me explain how LangCGT decomposes graphs. The important feature of LangCGT is pattern matching on graphs. So in this, for example, in this example, the x is bound to 1 to 3. Then we can track the graph node in this function. And the following case itself is 1 and 2, and not 3. So again, we want to run this program on our interpreter. Yes. Here we have a different list. 1, 2, 3, 4, 5. We also have a function. Yes, we also have a function, and applying the difference to a function outputs a new difference list. Cons 1, 2, 3, and 4, no 5. Okay. Yes. In the previous research, we gave a homosynthesis matrix to LangCGT and design a new type system. To formalize LangCGT, we incorporate graph transformation to keep the type and 4 values down the calculus. To do so, we employ formulation of hyperlink. Hyperlink is extended from elemental to allow hyperedges. I gave homosynthesis matrix to this. We are now using this to formalize LangCGT. Hyperelemental is quite different from ordinary graph construction. Hyperelemental handles post hypergraph with very unique. Instead of using graph isometric, equivalent of graphs are defined with structure method, which we also found in Poskitt diagram. Then matching and rewriting can be defined in a very simple way. We will show today. Integrated approach of Hyperelemental has half-90 standard mainstream program languages. I believe so. So LangGT handles graphs analyzed in Hyperelemental. So let me first explain the graph Hyperelemental. Graph in Hyperelemental can be an empty graph or a vertex with length and length x1, x2 to the xn. Link connection, composition of subgraphs or a high of length. For example, the differences can be represented as follows in Hyperelemental. You can see that there is a constant one. Comes with Scherp numerous rows. These rows find equivalence of graphs. I don't explain these rows in detail, but if you are familiar with Poskitt algebra, you can find these rows. You can find most of these rows in Poskitt algebra. Now let me explain how we extend it. Non-calculus with Hyperelemental. LangGT handles graphs in graphs, but it's also a functional language, so functions are also Poskitt. So therefore we extended Hyperelemental graphs so that graphs can have non-abstraction embedded in those names. We also extend number expression so that the data have graph in place with a graph with variables. Here is the syntax of LangGT. Boundary LangGT is a graph in Hyperelemental. We also allow construction and number extraction for the name of nodes. LangGT program is expression, which are either case, application, or template. We use template value with variable department. So semantics of LangGT is that of simply for simple forward value down factors, extending its substituents to substitute not just terms but graphs. Extending its space expression with pattern match, not just physical space, but graph. Here is the semantics of pattern matching done. For example, we match was 1 to 3 with this template using a substitution that replaces x with 1 and 2. Here shows the full list of action rules. The first one is what we have shown in the previous slide. The second one shows what will happen if we fail match. The third one is a brief reduction, which we have extended values in graph. The last one is standard in picture semantics. Picture formalization of small set semantics. We decided to build a concise frequency computation that will lead to sorry. In order to implement that correctly, we need to take care of some corner cases. These are not. So here again shows the last element moving example. In order to run this program, we have to pattern the template. This will be find a substitution that's by this integration. And If the graph is point 1 and point 2, then it can be matched as follows. You can match 1 with y, point with y, point with point, and 2 is z. It's not that difficult for now. But here shows the corner case. If the graph is only constant 1, then we can't not match like both. Here we try to match 1 with points and 1 with this, but we left y. So what should we do? For this time, we have to apply fusion, which is a special feature to reconnect. Special feature for reconnection. This example is applied we can match y with applied fusion. So this was the main difficulty we faced, but somehow we managed to do it very fast interpreter. Somehow we managed to do a reference interpreter in only 500 lines of code. In addition to the core syntax in the previous slide, we also implemented that direct. Because of that expression and also some primitive arithmetic operation. We also implemented a visualizer. Here is the image of the visualizer. You can click a run button to start running a program from the beginning. You can also click proceed button to proceed one step from breakpoint. You can specify breakpoints by using built-in plugin functions, which are just identity functions, but they display the input of the function of the right function panel. So here is our final demo with the function. Higher the function. This is a function that maps a function on a leasing tree. So this map function takes a function f a leasing tree x, then it must be applied the function f to every piece of the tree with the marker from very left to right. I will show this on our interpreter screen. So, here is the input leasing tree. If you want to apply the function of the successor function, we can here which returns the successor of the input number. And the leasing tree has 1, 2, 3, 4. Where is 1, 2, 3, 4? Applying the function. Applying the function of the new leasing tree with numbers 2, 3, 4, and 5. This was our final demo. There are several objects on functional languages or algorithm systems featuring graphs, but as far as we know, none of them generalizes majority types graphs are used. Anything this requires instantly, which the implementation was not trivial. So far we have implemented a new pure functional language, which handles graphs as part of data. For the future work, we are planning to implement a head checker so that we can gather some useful information to implement a more efficient function. We're also going to add ownership to the tax system so that we can ensure safety over the track rewriting for data. So the That's all for my presentation. Thank you very much.
Thank you. Questions? Okay. What about confidence? So,
Yes.
are you always confident?
No, not really. So it's undeterministic because of the pattern matching. Yes, this pattern matching can be done in a very undeterministic way in this matrix, but our implementation just gives the one of the solution that is much certain. Yeah. So this matrix is undeterministic, but by implementation, that's one of the solutions.
So how is that being picked?
So it just the first one. First is the one.
Okay.
I had a question about the type checking. So, trying to understand what the types would include. Are they types for the different shapes of graphs, or just types that make sure that what you get is actually graph?
We try the type system using graph grammar. I understand. Other types can be considered as regulatory grammar. So we decided to then the other data types with any regular graph grammar, so that we can define custom data types for example W.
All these subtypes of graph. But obviously you can define links. Obviously you can define lists and things like that, but these are all subtypes of graph. Right?
You need now define the type of that represents every kind of graph, right? If I use regular graph grammar, regular graph grammar represents every graph. So it's kind of something restrict. That's your question. Right.
I just try to understand the type checking. But I think I understand. So I understand what you're saying. So you can define specific type of graphs. You can kind of generate them inductively, like particular constructors and so on. So maybe the only question really on top of that is, are these in your type system all subtypes of graphs, or are these specific types for lists and for trees and for other type of lists?
Our type system relies on regular graph grammar, and this regular graph grammar is I think that it's extension of regulatory grammar. So, for example, it can represent like the paragraph. So the regular graph grammar is kind of linked to some extension to trees. That's my understanding, but I want to hear your answer. Because I'm not
I'm just thinking of what people do in shape analysis, for example, where you find well, there you basically start out from graphs as a general data structure. Then you say, okay, so there are some graphs that represent lists, and there are some graphs that represent particular types of trees or other, or even sometimes floating from straight like a cyclic graph and things like that. But they are not technically types in a programming language sense. They are more constraints on graph. But I was wondering whether in the type system here, you can actually define particular shapes of graphs, let's say, as subtypes. So that would be interesting, but I think that maybe something new.
Yes, I don't think there are lots of things as types of whole graphs. Yeah, it's pretty predictable now. Yeah, it's just I think very natural and disruptive extension to ordinary LEDs.
I think graph is much better than the software verification. So software verification is difficult for a programmer to use, but type system can be automatically checked by the compiler. So it's very useful. It's very easy to use for programmers. So I think this is not
Okay, but I understand.
Have some value happen
Yeah.
in a draft.
Yeah.
How do you manage that? That is.
Yeah.
What can you convince? The Poskitt is.
Okay, we haven't considered this. We haven't considered any kind of complexity or extensity yet. We are thinking of that. If we enter type checker and get the information from type checker, we can because type checkers allow kind of extension of trees. So it must be much easier than the general graph mapping. So that's our plan.
Questions? Adrian, how do you compare to clean language?
Clean language, okay.
Because they have a very sophisticated type.
I think clean language cannot clean language cannot handle mathematics as we do. For example, mapping the last elements of this is not. I believe it's not possible in language. Is it possible?
I guess so. Really? I don't know. I don't know. It was in 90s.
It's not possible. It's not possible. Also, we allow users to find a custom data type to enter the text structure. For example, that which is I still believe it's not possible in plain language. And also, we are going to implement a type checker with ownership check. In this, we believe that we do not need double correction. That is the one of the difference between some ordinary functional languages and our language in the future.
And do you have a language to express the strategies of rewriting?
You mean so
like Stratego and so?
strategy?
We have different rules.
Yes.
And can you define a strategy how to perform these rules?
I understand correctly, you mean like the matching property from the very top and just fails this goes to the other side. So there is no kind of very rules so that will be highly long term. Is answer.
Okay, we can continue discussing later.
Okay, I see.
So it's time. Thank you again. So the next speaker is David Richerby, and we will speak about computing k-Bisimulations of large graphs.
Somebody get me my slides. You take the left. Yeah. Now, obviously, what I need to do is start facing this way. And wait for everyone to run. But I will be presenting from the laptop, so. I'm sure there's a movie, possibly a cartoon, in which some character keeps turning around and everyone keeps running from one side of the room to the other. If only I could remember which one it is. But we could reenact that.
It could be you.
I don't think I'm in any movies. Nobody's told me that I'm in any movie.
You're on a YouTube live stream.
Yeah, but the video's off, so it's technically not a movie. Okay, so we have slides. So what I'm going to talk about this afternoon is joint work between myself and Jannik Rau, who at the time was an undergrad at Ulm University. The work here actually is basically his bachelor's thesis, and it was supervised by Ansgar and me. Unfortunately, Jannik has been lured away by the salaries offered outside academia, and is now having fun working for a software startup, and we're here presenting his work. So this is kind of graph transformations in the broadest sense, in the sense that I'm going to be talking about algorithms whose input is a graph and whose output is a different graph, right? So it's forming a graph into an graph. So the context is that we are interested in summarizing large graph databases. So we had a couple of talks this morning mentioning graph databases. Essentially, from the point of view of this talk, you can imagine that a graph database is just a graph, and the vertices and edges have labels, which we'll use to store the data. For those of you who are from that community, you'll see that I'm kind of ambiguous as to whether I'm thinking of label property graphs, or there'll be a point at which you'll say, haha, you're doing RDF graphs. But really, it doesn't much matter. And when I say large, I mean, up to at least billions of edges. And what we've done in this work is we've compared two bisimulation algorithms from the literature against an algorithm that we developed ourselves, or rather, which was developed in prior work by some of us, which is more generic than just bisimulation, right? It can do more things than just bisimulation, but one of the things that it can do is bisimulation. So what we were interested to see is just, how well does this general purpose algorithm compare to using a specific algorithm designed for bisimulation. Okay, so what is graph summarization? So we've got this enormous graph database. We want to run queries on this database. Running queries on a large data structure is going to take a lot of time. So what we're interested in is producing a smaller graph, which contains all of the information that we need to answer the queries that we're interested in. Okay. Now, what we're not doing here is graph compression. Okay. So, although in the terminology that we use, I would describe what I'm about to show you as a lossless summary, but that's lossless with respect to the thing that you're trying to do. Okay. It is throwing away some information from the graph. So from this summary, it might not be possible to reconstruct the original graph. And the key thing that we're going to be doing is that we're going to be defining equivalence relations on the vertices of our graphs. And essentially, we're going to merge equivalent vertices into single vertices. So you can see how that would make the graph potentially a good deal smaller if a lot of the vertices are equivalent to each other. it occurs to me that I don't actually have a slide showing you what the output graph will look like, which is possibly a poor choice. You can to some extent think of it as a quotient. It's not literally the quotient of the graph. So the quotient of the graph would be merge all of the equivalent vertices, and if there's an edge between a vertex in one equivalence class to a vertex in another equivalence class, then you have that edge in the quotient. The summaries that we produce are a little bit more complex than that because our definitions of the equivalence relations are kind of nasty. So we'll define vertex equivalence based on, well, are these things equivalent like this, and are those things equivalent like that? And our summary needs to include all of that information. Okay. So just to give an example, here is my large graph database. It has billions of edges, specifically 0.0000008 billion edges, but that's a number in the billions. And how might we be interested in summarizing this? Well, in fact, there are all kinds of different ways that you might want to summarize it, right? You could look at all of these entities on the top and say, well, all of these things are entities that have a name and they work at a thing which also has a name. So all of these are cool. That would be perfectly reasonable for answering some queries, right? If you want to know how many people there are in the world of academia, then that would be absolutely fine. On the other hand, you might want to distinguish between students and members of staff. You might say that, Ansgar and I are equivalent because we're both academics, and Jannik is in a separate equivalence class because he's a student. You might want to say that Jannik and Ansgar are equivalent because they're both at the same university, and I'm the odd one out because I'm at a different university. So depending on what queries you want to do, there could be all kinds of different equivalence relations, all kinds of different summaries that you might want to produce. So this sort of recipe for turning a graph into a summary is what we call a graph summary. And as I mentioned earlier, that's basically a sort of recursively defined, or rather, it's an equivalence relation, which for us is going to be recursive. And it's going to be recursively defined in this language, which we call fluid, which I'll say a little bit about. But basically, the generic algorithm I mentioned that we're going to compare against these single-purpose bisimulation algorithms is this algorithm here that can process a description of an equivalence in fluid and spit you out the summary graph from your output. So this is joint work by two of the three of us, plus Till Bloomer, who is a now graduated PhD student. So the main way that fluid produces these nested definitions of equivalence relations is through this thing called a complex scheme realm. And this is the point where you might notice RDF creeping in. Don't worry, if you don't know what RDF is, you don't need to know what RDF is. So complex schema elements define an equivalence relation based on three sub-equivalence relations, right? And these sub-equivalence relations are going to need to be represented in the summary, which is why the summary. So in the world of RDF, we define edges in our graphs, having the usual terminology being they link from a subject to an object vertex via some predicate. So that's where these initials are. So they're going to say that two vertices, what do I call them, B and W, are equivalent if, first of all, they're equivalent according to this subject equivalence relation. And that would be some relation defined by some other term. Furthermore, So they've got to look the same locally, but they've also got to have the same sorts of connections to the rest of the graph, right? So if I'm going to be equivalent to you, not only do we have to be equivalent locally, but also for every connection that I've got to somebody else, you must have an equivalent connection to an equivalent other person. Okay? And equivalent connection is defined in terms of this predicate equivalence, and equivalent person is defined under this object.
You say connected, you mean outgoing connection?
I mean outgoing, yes. Later on, I might mean incoming as well, but yeah. Yeah. The triple is very much like RDF. So you'll only look at nodes, but predicates themselves might be nodes in the graph, if you see what I mean. Alternatively, just think about it in terms of label property graphs, and then this predicate equivalence just means the two labels are equivalent by whatever means you're describing labels as being. Okay, so that's sort of graph summarization in general. The specific summaries that I'll be talking about are based on bisimulation. So bisimulation came out of the world of labeled transition systems and process calculi and things like that. What's a labeled transition system? It's just a labeled graph. Right? Yeah. In this case, the vertices of the graph would represent states of a system or something, and the labels on the edges would represent how you can get from one state to another, but it doesn't matter. And the idea in bisimulation is that we're going to define states to be equivalent if they have the same behaviors, okay, if they support the same operations, but not just at the next step, right, for all steps in the future, right? So two states are going to be bisimilar if whenever you start at this one and apply a sequence of transitions to get to somewhere else, well, if you start at this one and apply the same sequence of transitions, you'll get to somewhere that's equivalent. So how's that defined? Well, we end up with an equivalence relation where two vertices are equivalent if for every edge coming out of the first one, there's an edge coming out of the second one with the same label and leading to equivalent states. Okay. And this recipe here is, I've said it's very similar to a complex schema element. It's in fact almost just a special case of a complex schema element, right? We've got the same universal existential sort of mimicking. I suppose the other thing to notice about that is that I've been a little bit loose here. The way I've defined this, if anyone's still awake at this time in the afternoon in this rather warm room, if you just declare every vertex to be equivalent to every other vertex, this property will hold. So actually I need a restriction that it's the finest possible equivalence relation on your graph that has this property, right? So you can't split any of the equivalence classes into smaller equivalents. Okay, now, bisimulation as a whole considers sort of all futures out to arbitrary depth, okay, and says that two vertices are equivalent if, you know, they support the same operations forever, which isn't necessarily what we want to do. So there's this concept of stratified bisimulation, which is basically bisimulation out to a fixed distance. You know, the idea being sort of that suppose I want to distinguish me from you. Well, if the only way that I can distinguish the two of us is that, my aunt's mother's, babysitter's, cat's first mouse that was caught was black, whereas your, whatever I just said, mouse was white, they're kind of really the same. There's not much that divides us. So the idea here is just to take that idea of bisimulation, but just to cut it off at some point where we kind of stop caring about the difference. So we'll define bisimulation out to distance k inductively. So bisimulation out to distance 0, we just say that, well, if you don't look at anything, anything is going to be a 1. Okay, so we're going to say that all vertices are equivalent to level 0. But then we'll say that vertices at level k plus 1 are equivalent if, well, firstly, they were already equivalent at level k. And secondly, if you do this thing of looking at neighbors, every neighbor that one of them has with a particular label, the other vertex has a neighbor with the same label that is equivalent to level k. Oh yeah, and I should mention all of these are vice versa conditions, right? They're completely symmetric. Now, for any given graph, the full bisimulation that I described on the previous slide is equivalent to k-Bisimulation for some k. Right? Basically, if you take the diameter of the graph or something like that, then any path longer than that must wrap back around, and you can't make any new distinctions by looking at those. So for any given graph, the full bisimulation is k-Bisimulation for some k, which is quite handy, right? Because you can see how you could compute this. You can compute k-Bisimulation and keep going, whereas if I asked you, where is page up on this laptop, if I asked you how are you going to compute that, that's a little bit more mysterious to compute full bisimulation without knowing that you can go through k-Bisimulation. So just to bring back the example, let's look at k-Bisimulation on this graph. And so I'm going to denote the equivalence relation just by listing its equivalence classes rather than listing the. So as we said in the definition, all vertices are equivalent at level 0. But then you can see that, for example, this node JR143 is not equivalent to the node Ulm University because the node JR143 has a worksat edge coming out of it, and the Ulm University vertex does not. So if we look at one bisimulation, then we find we get these 3 equivalents, okay, which correspond to the top row, right? All of these vertices representing people have a name edge and a worksat edge. These two nodes representing universities, Ulm U and UOE, they have a name edge but no worksat edge. And finally, the literals, the things in strings, they're all equivalent to each other and to nothing else because they have no edges at all coming in. And it turns out that for this particular graph, right, if we go to any higher level of stratified bisimulation, actually we just get the same answer. Right? We can't make any more distinctions. Okay, so that is one version of bisimulation. There are actually a whole bunch of others. So forward versus backward bisimulation is exactly what you were asking. Am I looking at edges going out or edges coming in? Also, the bisimulation that I just defined didn't use the vertex labels at all. Well, you could use vertex labels instead of edge labels. And in fact, you could use any combination of these things, right? You could consider both forward and backward with both edge and vertex labels. I suppose in principle, you could consider no labels at all. It probably wouldn't be very interesting. I think two vertices would be equivalent if and only if they had a path of length k coming out of them or something like that. But you know, you can do that if you want. So what's the connection? Well, it turns out that a lot of graph summary models that have been used in the literature are actually versions of bisimulation. Now, maybe you want to say that this first one is a little bit trivial, David. So class collection says that two vertices are equivalent if they've got the same labels. Okay, but that is actually exactly what zero bisimulation is in the world where you're considering vertex labels. Because in that world, instead of saying that initially all vertices are equivalent, you say that at the first level, vertices are equivalent if none happens. Various other ones, just to note here that the LODX loop and SchemeX look exactly the same in this world. That's because I've missed off some details that do make them different. Basically, they differ in what you do after you've computed the bisimulation. Here's an example term picker that uses both both edge and vertex labels. And then here are a bunch that are essentially just k-Bisimulation. I suppose top fit, if you avoid naming your thing, then people who give talks about it have to mention your name. Whereas if you name it, I'll just use the name, which is another way of saying this slide is not large enough to credit all the researchers involved. And now just to fill in one of those names, right, because the AK index was one of the ones on the previous slide. So AK index is a vertex labeled backward bisimulation, and I'm short of time, so I'll skip the details. Just to briefly discuss how their algorithm works, let's call an equivalence class a block because it's much shorter. It looks at the relationships between blocks. In a bisimulation, everybody in one block either has edges to another block or does not have edges to that block. In a partial, on the way to computing bisimulation, you'll find that you have blocks that have some edges, some vertices have edges to this guy and some do not. And it splits the blocks like that. Schätzler et al. Have an edge labeled forward bisimulation, basically computed by a MapReduce technique. Rather than splitting blocks, you define a signature of a block that basically says, what do your neighbors look like and what are your connections to them? And you iteratively refine those signatures. Our generic algorithm will do more than just bisimulation. It's broadly similar to Schätzler et al., but there's more to keep track of because there are more reasons that the vertices may or may not be equivalent. And one thing that we want to do there is sort of track the complete type of the vertex, but that basically involves saying, what is the subgraph centered on this vertex, which could be exponentially large in K. So for this work, we're going to hash it. We had reasons to store that entire structure before. It's not just because we didn't notice it could be exponentially big or something. Okay. So in the last couple of minutes, what did we do? So we implemented these algorithms of Kochik et al. And Schätzler et al. Compared them against our generic algorithm defining the same bisimulations. I think it is worth mentioning that Kosiol and Schätzler do compute different bisimulations. We're not trying to compare Kosiol and Schätzler against each other. We're just trying to compare them with us. You know, you could equally well use Kosiol's algorithm for computing Schätzler's bisimulation, or vice versa, but we chose not to do that. So this is the running time of our algorithm so we're going to compute 10 bisimulation, which requires 10 iterations. These are the times per iteration for the various algorithms. So the dotted lines are the original algorithms, the solid lines are our version. I apologize to anyone who's colorblind. I only noticed that when I came to make the slides and it was a bit too late. The orange line is the two versions of Schätzler, and the green is the Kosiol. Main takeaway here is that, well, ours is actually faster per iteration. Schätzler and ours have roughly constant time per iteration. Kosiol's algorithm does not, because it's doing all of these block against block comparisons. So it depends how many blocks there are in the current simulation. I should also say that this is, you know, don't look at this graph and say, sheesh, Kosiol's awful. They produced a sequential algorithm. These three are parallel. We're running on a 32-core machine. That's why this one is much slower than these ones. We looked at a couple of other data sets. One thing to mention is that Kosiol does have a termination condition, which means it can stop. On this graph, actually 7 bisimulation is everything. So the older algorithms waste 3 iterations, not changing anything. And this is running on our largest data set, about 2 billion edges. Unfortunately, Kosiol on that one was just too slow, being a sequential algorithm. Okay, I think I have actually mentioned all of those points. The other point to make when comparing our generic algorithm against these specific ones is that it did cheat very slightly by just quoting the iteration times, because our algorithm has an initialization step that takes about as long as an iteration, that needs to be done once before you start. So what we actually find is that if you want to compute a 5 bisimulation or more, our algorithm is faster, even including the initialization. If you're computing a 1 or 2 bisimulation, the others were always faster. And there was some point between 3 and 5 where our algorithm overtook. Yeah, so in conclusion, because of the way that it exploits the parallelization, our generic algorithm is actually faster than the single purpose algorithms for computing at least a k greater than 5 bisimulation, and in many cases even for a 3 bisimulation. And you can kind of say, well, we've basically parallelized their algorithm, right? Because we've produced a parallel version of it. A couple of items of future work. Part of the reason that we were carrying around these great big vertex signatures in the original version of our algorithm is that allows us to do incremental computation. So you change the graph, I'll update my summary. We don't know how to do that in the hash-based version. It should be possible. And the other one is it would be nice to introduce Kosiol-style termination checks. Kosiol is very easy. If you fail to split any blocks, you're done. For us, it's more about detecting have any things that used to be together been split apart, which turns out to be a bit difficult. All right, I'll finish. Thanks.
Yeah. Okay.
Is there a condition for the example that you mentioned? someone's pet,
Oh, yeah.
someone's mouse or something
Yeah.
like that. I mean, that is of course not just a question of death, but also a question of what are the labels that you go along in order to, what do you think are the relevant?
Right, yes. You could also argue that if a chain of 6 hops that are based entirely on this person is related to this other is sounds more reasonable than one that has to go through cats and mice, yes.
I wonder whether the kind of generic way of specifying that is some sort of path expression, where you say, here's a path expression, if you satisfy, and a path expression can include nodes,
Yes.
labels.
Yes.
And then you say if they are equivalent, as long as you follow sub paths of their path expressions, then I consider the path expression representing the significant or the relevant.
You
Just in the sense of the relevant path, then I consider it equivalent, and everything outside that path expression is I can ignore.
You can try to do something like that. I think that there are some summaries that are based on path expressions rather than on this kind of stuff. The thing is that, at least as I understand them, path expressions don't. Essentially, there's a difference between paths and trees. So if I've got a red edge to 2 different vertices, which the first has a black edge and the second has a red edge, that's different to having a sort of Y-shaped graph with the same colors on it. Do path expressions distinguish that?
And there are path expressions that has them with alternatives.
Okay.
Yeah, but there's sets of traces essentially
Okay, so but without that tree structure.
without the tree structure.
Okay.
But that would come up during the bisimulation itself. You would still check all the edges with the labels that are alternatives at that point. That can happen.
I mean, otherwise, you're probably talking about something like CTL.
Potentially, yeah.
You want to specify.
Specify trees in all their.
I guess there's slightly more sort of the general, so you can think of sort of more or less expressive languages to describe these things, but I'm interested in sort of how much of this is, I guess, domain specific or model specific, because these path expressions would probably be specific to the problem or specific to the data model that you have.
In something like that, yes, where you wanted to say that cats are less important than people. Apologies, sorry, YouTube. Then that I think would probably have to be
a lot of the other
domain specific. Yeah, I mean, I suppose you could try and learn that stuff, but on the other hand, how do you know if is a rare edge really important, or is it really irrelevant? Right? If I'm the only person who is the son of the king, that's probably quite important. Whereas if I'm the only person who has a collection of 500 1950s comics, that might be less relevant in some situations. So,
Yeah, different question. So your algorithm is hash based, which means you might have hash collisions, which means it's an approximate algorithm. So maybe
yeah, this is true. Yeah, we kind of sweep that under the carpet and assume that the hashes are big enough to avoid collisions and stuff
right.
like
So
that.
you don't. So
In a sequential world, you can avoid hashing and just sort of assign unique IDs. But if you want to do that in parallel, that gets much more difficult.
Yeah. Okay. So that the hashing might result in you compacting too much.
In principle, it could lead to you thinking that 2 things are equivalent when in reality then.
That's a strong question. I'm not that knowledgeable regarding k-Bisimulation, but what you have is project came basically down the hill and then it went up again. So what is the intuition behind that?
So I think the intuition is that probably here there was a lot of splitting going on. So the actual work of the splitting was significant. down here, you probably had a lot of blocks, but they weren't splitting very much. And then as you come up here, you're getting more and more blocks. I suppose I should mention there's also an optimization in here where we track which blocks you've already used to split. Because once you've used a particular block, you never need to use it again because you've already distinguished vertices on whether or not they talk to this one.
Because I would have expected to see something down there, but maybe it won't detect the line.
Yeah.
So you mentioned state somewhere in the presentation. So can you mathematically compute the state?
I'm not quite sure what you mean. So the way I mentioned state was that label transition systems are looking at program states, but they're looking at them in, and this is out of my wheelhouse, but I believe you're looking at them in a pretty abstract sense. And it's just, you've got states 1, 2, 3, 4, 5. If you're in state 1, you can do this kind of transition to state 2. If you're in state 2, you can do that kind of transition to state 6. And things like that. So states in that sense are, I think, sort of atomic things that you would look inside.
They don't have the transaction.
I don't know, I think is the most honest answer to that question.
Okay, thank you.
Okay.
By Lars about advanced efficiency operation with high order. Yep.
Yes.
PowerPoint.
Yes. One second. Ja, das wurde.
Okay, just go. Okay, so I believe I have the honor of having the last presentation for this year's ICGT. My name is Lars, and what I want to present to you today is what we refer to advanced consistency restoration with higher order shortcuts. So when I talk about consistency, what I mean is consistency between two models which do not necessarily have to move very much alike. Here on the left, we have a meta model defining basically rows of houses where you can have a house and the house may have a reference to the next house in line. And each house stores information about which architect designed that specific house. And you have some house types where you can think like you ordered this house from some catalog. So we can have a nook house, a villa house, or a cube house. And on the other side, you have something which looks quite differently, where we say like, how are these houses constructed? So you make a plan where you say, okay, we've graded that plan. And then for each house, we want to have some construction that basically describes how to construct that specific house. Yeah, and you have some company who's assigned and responsible for building that specific house. And these construction steps then tell you how to build this house. Like first you want to have maybe a cellar, then some floors, and at some point maybe something like a cellar roof. So, and we want to say that these are at some point, or similar manner, they are a bit the same. Like for each house, you will have some sort of construction on the right side. And currently there's no means to express something like that. So usually what we do is we create a 30-meter model in the middle, correspondence meter model, which enables us to do exactly that. And in this part, what I want to show you is if you have some models which are at some point consistent, how you can propagate changes in a way where you do not lose information along the way. Okay. So, and as our tool of choice, we employ triple graph formats, which are a declarative way on defining what consistency between these models means by a set of graph grammar rules. And this first rule here, look rule, and what it basically tells us is, so you can see that all these elements are here in green and annotated with a plus plus. So if you apply this rule, it means that all these elements are just created. And this rule states that you can create a new row of houses. And that means that the first house always has to be a Nook house. And what you have to do on the other side in the target model, you have then to create the plan first and first construction for this Nook house. And apparently every Nook house only consists of the floor. So it's quite easy. And if you have done that at least once, what you can do is you can apply something like this cube. You would see here, where you state something like, okay, given that you already have a house and a plan with a construction on the right side, which is depicted here as a precondition on black, then you can create the next house in this row of houses as a cube house, and the cube house has a cellar and then the floor. And similar to that, we have another rule, the villa rule B, where we say something very similar, but the villa rule has a floor and then a cellar. And it is, of course, a toy example, but as you can see, it's gonna get quite complicated when we start propagating changes. But first, what these rules actually just do is, when I apply them, I just create source and target models from scratch, which is usually not what I want to do in practice, right? So you're given, for example, some rows of houses, and you want to translate them to get the other side. So in order to do that, you can operationalize your TG rules to obtain something like these forward TG rules, where you say something like, okay, we are giving these houses, so we do no longer create them. These elements on the source side, on the left side, become black. And instead of creating them again, what we do is we mark them as translated, which is here indicated with these little boxes. And upon application, what you do is you create the missing structure on the other side. So that's, give you an intuition on how this works. I have a very small model here consisting basically just of two houses here on the bottom. So you have a Nook house followed by a villa house. And on the right side, you see what we call a precedence graph. And this is of particular interest for the rest of this talk because it tells you the state of consistency of these models with respect to our triple graph parameters. So basically, each node stands for a rule application. And here, this first node that you see stands for an incomplete Nook rule application, where up we have the label for the corresponding rule, and the left little box with the plus basically states the state of consistency on the source side, and the right box with the use states consistency on the target side. And this plus tells us that this element, this Nook house, is completely new. You probably want to translate it. The U on the other side tells you it's basically undefined. You're not sure what is there. At least you do not know, oh, there is nothing on this side. And very similar to that, for the other node that we have, we know, okay, it's a incomplete villa rule application. And this edge between the villa rule and the Nook rule application basically tells that before you can translate villa, you have to translate the Nook rule. So let's do it. We translate this Nook house using Nook forward rule. We create the missing element on the right side. We create the plan, the construction, and the floor. And then we apply the villa forward rule, translate the villa. And as you can see in our precedence graph, these little markings have vanished. We just have blank boxes. So we restored consistency, which we translated the model. But as you also can see, there is no information about the creator of the plan, maybe me,
And also there is no construction assigned, no companies assigned to each construction, which is only natural because there's no information which is present on the source side, so I cannot derive it out of thin air. Well, what I can do and would probably do at some point is could insert it manually. So I have done that, and now it gets a bit more interesting because now we're gonna change this model, the house on the left side, and propagate these changes. And I want to show you how it was done before in a trivial way and the problems that arise with if you do it like that. So I changed the model. I add a new first house in this row of houses, a new nook house. The former nook house I make to a villa house, and the old villa house I make to a cube house. And again, I can see on the right in my precedence graph, I can see the state of consistency. So these two nodes I knew from before, they were intact. Now they are no longer intact. And I can also see in my precedence graph why it is like that. Because there's an attribute change on the source side. Because when I translated the nook house, I expected it to be a nook house, but now someone has changed it to be a villa. However, at the same time, I have new rule applications that tell me basically how to, not which elements have been broken, but how to translate them instead. So for this new nook house, I have again some new rule application, some possible translation. And I also, for these broken elements here of broken rule applications, I know that probably you would want now to translate them, for example, using the villa rule or the cube rule. You want basically to replace them. And how we synchronized that before was basically, so first you will probably start to translate the nook house on top. So we do that, use the nook forward rule. And now you're basically stuck because you have some inconsistencies and they block you from retranslating these elements. So what we do is we simply revoke these former rule application steps, translation steps, delete all these elements, and then we are free to retranslate these elements again using our villa forward rule followed by the cube forward. And now what we have is we have again restored consistency, but at cost, because there are 3 points that I want to highlight for you. First, the plan and the plan has no creator and no company has any company, no construction has any company assigned to them. That's the first thing. So I have lost information. And another thing is, if you think about just adding one new house to a very long row of houses, then you will probably have to retranslate all these houses again, which is pretty inefficient. So you probably want to avoid that. And last but not least, and this is basically where, which leads us to a solution to the problem. If you look at what we have now, it looks very similar to the model that we started with. So we still have one plan, we still have one construction for each house, and each construction has exactly one floor. So you might ask yourself, so why did I take all these actions just to reach the state where basically we started from? So if we just take a step back to the point before I started synchronizing anything, then you will see what I pointed out earlier, that I do not only have information about the things that have become inconsistent, but also of the things, basically the place where I want to transform to, how I want to repair things. So I want probably to replace the nook rule application, which has been broken, with a villa rule application. And in another work of ours, for that purpose, we introduced what we call shortcut rules that basically replace a broken rule application with an intact one, where you take, for example, here the nook rule and the villa rule, and what you do is you overlap them, and thereby you can identify things that they have in common. So if you want to transform from the one to the other, you do no longer delete a lot of elements, but you do only delete those that you did not overlap. So you can make this in a much more clever way. And again, you can operationalize these rules that we have seen before, and then propagate a complex user change. And what we found out very recently is that it's not always enough to repair one rule application at a time. Sometimes, as in our example, and you have to believe me on that, you have to repair multiple steps at a time to really to be able to preserve as much information as possible. So in our case, what we do is we analyze our precedence graph. We try to find out which inconsistencies are related somehow. So for example, like here, we have this NUC rule application and pillar rule application, and I can see that they form a cluster of inconsistencies that are somehow connected. And at the same time, I also have information about where I want to repair to. So what do I want these broken rule applications, how I want to replace them. And I also have a cluster here. And our idea is then to take this information, build bigger TG rules, and again overlap them to create basically bigger shortcut rules and repair even more information than before. And for our example, what this means is that I have to build two rules. Basically, the one that represents my broken rule applications. So I started with a NUC rule application followed by a Villa rule application, and I concatenate them together. And then I invert them, because basically what you want to do is you want to remove this broken rule application and replace it with something else. So you have this is the replace rule, and on the other side, you have the rule applications that you want to replace these with. So we have here, we know in the end, we want to have a NUC rule followed by a Villa rule and then a cube rule. And again, you concatenate them. And then what you do is you overlap them. And it's not just doing this by random. We have at least a bit of information, because we know that this NUC element here on the left is now the Villa element on the right. We also know that the cube element here, it's the Villa element here, has to be a cube element on the right. And for the rest, basically it's an optimization problem where you try to overlap, or you try to overlap as much as you can to preserve as much information as is possible. And if you do that, what you will get is a rule that should look similar to this. So this is our higher order shortcut rule. And what it tells you is that you can add a new NUC house to an already existing row of houses by adding this house here on the left. And on the right, you create a construction and the floor, but you no longer have to recreate this plan, because basically what you do is you just steal it from the villa, which was formerly a NUC house. And we also know that the villa house was formerly a NUC house, so we have to create the cellar roof, which is obviously missing. And we know that this cube house was a villa house, so we have to get rid of the superfluous cellar roof. Instead, we know a cube house has a cellar, so we create it. Yet, as before, you can see these changes are on both sides again, but we know that the user already did these changes on one side, and I want to propagate them. So we again operationalize this rule. Elements on the left side, which were green, are now becoming black. We mark them as translated. And then we can apply this rule to our model from before. And we store consistency in just one step with the application of this single rule. And the difference to what we had before is that first, the plan has still a creator, which makes sense. I just added a new house. I still have the companies for the houses that I had before, which is probably reasonable that only because I changed the type of house, it's probably still the same company. And for this new house, there is no company assigned. I have to put this information manually as I had before. However, so it was a much more efficient way to do. So that's a rough idea. I just want to wrap it up. So what's the construction process, or at least in the sketch? So you always start with your annotated precedence graph, and we obtain this one by using incremental pattern matching, where we basically detect all these locations where you can apply some sort of TG rule, and also we can detect inconsistencies. So if you change something, we can detect these inconsistencies and match them to the match that you had before. And you reverse over this precedence graph, you try to find clusters of inconsistencies, and then you create your replacing rule and your replaced rule to create a higher order shortcut rule. And for that purpose, we employ ILP solving, because basically you want to find a maximal overlap. Maybe you want to even prefer some overlaps over others if some information is just more important than other information. So it's an optimization problem. then you operationalize it, and then you can just apply this rule basically to fix the inconsistency. Yeah. That's so come to the conclusion. So I showed you our new higher order shortcut rule framework, which is based on a runtime analysis. So basically, a user changes something in the model. We create these higher order shortcut rules on the fly, looking at the situation that we see there. Shortcut rules are formalized, so the construction as well as when it is safe to apply them, and the conditions are not too strict. As you saw, these rules can preserve information, and they at times can even increase the performance when you do not want to have these cascades of retranslations. And we implemented this in Imorphom, so it's completely automatized. So basically, when you use RTGs, it is somewhere in the back working for you. And there's also a VM, which is referenced in the paper, where you can just try it out on yourself. We release with one click our benchmark results. And for the future, what we would like to investigate are whether we can identify maybe statically situations where you do not really have to create these higher order shortcut rules, because in some cases it is enough to just repair one rule application at a time. So you do not always need this overhead that obviously comes with this analysis. And last but not least, there are situations where you do not want to just propagate changes from one side to the other, but where you have changes on both sides simultaneously from independent developers, and where these changes may be in conflict. We would like to investigate if we can also apply these rules in this use case. And yeah, that was my talk. I hope you enjoyed it, and I'm open for any questions. It really depends. So considering these examples, so if you have a component rule set, then it's okay. So for all our tests, so we have a lot of TG tests, and we write it out, and it was almost a constant offset to every of our tests, basically, that you have to pay. However, the problem arises when you have some rules that basically are in conflict with each other. So in that case, when you try to find a higher order shortcut rules, the state space explodes, because you have to incorporate all these possible rule applications or alternatives that you have. And you have to basically tell the IP solver that there are all these conditions that you have, and he has to search for the best one. And then it gets much more expensive. But at least for these rules here, if you can, for example, by using negative application conditions and such, if you can use them, it's almost just a constant offset that you have to pay. It's quite nice. It didn't expect that.
Yeah, you said that that in some cases you have to look at more than one change at the same time when you build these, which raises the question. So suppose that somebody really applies these changes one after the other, and you repair it twice. It suggests that the outcome might be different if you repair it twice based on separate changes or once based on the combined change.
Mm-hmm. I haven't had such a case yet. I'm not sure that I can really answer that this is a real problem, that it can happen. Not sure.
I don't think your example showed us why you have to combine them, right? You told us we have to believe you.
Yeah,
I'm willing to believe you. That's not the point, but the very fact that you say it's necessary or better to combine them suggests that the outcome is different if you don't combine them.
Well, here the reason is, because, well, depends on how you see it. I think the problem is here that if one change, or if you had a couple of changes, but you only have one rule application that basically matches these changes, then then everything is fine. And I do not have an idea on how one change would basically invalidate a lot of these rule applications. And that might be something like what you mean. I'm not exactly sure. So it's very abstract, and I have not a real clue of how such an example would look like. And if that's really a problem, cannot give a qualified answer on that. Sorry.
They say that you have to deal with several changes at the same time. The example that you use, and I suppose that this is the case in general, it changes on the same model, so that the propagation goes from, in other cases, from one model to the other model. So otherwise, if you have more changes in the two models, then you have concurrent synchronization, which has a specific complexities, difficulties.
So you're referring to the future work that I mentioned, right? Or in general? Okay. Yeah, that's good, but I'm not, so currently it's just sequential synchronization. Yeah, and that's also the only thing that's working. I mean, if you have concurrent synchronization in that case, and you have these cases where changes are in conflict, then of course I'm not entirely sure how such a higher order would perform, because then you would have somehow to encompass conflict resolution with this rule. So I guess this would be something like you have first to identify the conflict, and then ask the user how to solve it, and then on what he decides to do, then build a higher order shortcut rule which performs the trivial, more or less trivial synchronization task, plus his preferences on how to solve the conflict. Then one step, maybe that's something which could be done. But it's just more like an open thing. I'm not even sure if that's reasonable. Yeah.
So it seems you're assuming that two attributes with the same name are compatible.
In that case.
In that example. But so suppose that on my street I have a YouTube studio, which has creator Lars, the guy who's running the YouTube channel. And I change my mind and I want to make it be a church. And now the creator field is going to be the person that gets worshipped at this church.
And you know,
that data shouldn't be copied. Well, I mean, in your case, that would be very but is there a way around that?
Currently not. So I would preserve it, at least considering that all depends. So I would expect that this is modeled like that you would replace the house with a church, with another maybe type. But if it really stays a church, that will be a problem. That you're absolutely right. Yeah.
Yeah, I was wondering if there's some kind of type system, maybe with inheritance or something. So bad, but
yeah, we found more situations where it is reasonable to preserve this information, or where you are really not satisfied with the result if you lose it. But I absolutely see use cases where you just do not want that.
Yeah, well, I can also see in most cases it seems like
I mean, it might be a very, very good configuration option that you could provide to user, like, okay, in some repair steps, you just know this. Yeah.
And certainly if it's all designed by the same person, then it's like, well, don't do that.
Maybe, yeah. Yeah, but you're absolutely right.
Thank you. Session, I would like to thank very warmly the co-chairs of the ICGT for the nice program they came up with. I'd like also to thank the organizers, Reiko and his team, colleagues, and students. Thank you.
But advice that
that capacity and sort of volunteer organize it. So yeah, thank from me and everyone else was involved and were to make it a success. And as an organizer, I mean, as I said before, I mean, people, I guess maybe the biggest part was others sort of sitting with the back space. The technology on well, I mean, it looked very smooth, but it was not trivial to organize, and we didn't have sort of a lot of time to practice. We sort of learned how to do the work over the first couple of days. So luckily, events at the beginning of the week were a bit smaller. We had patience to learn. Yeah, and then obviously, thank yourself for being very great for the work with the program. So he's basically been editing the web page in real time continuously for the last month. Probably. So whenever there was a little bit, so that's what I think of as a really idle. Whenever there was a little bit of information that was drafted. Yeah, and Roy, as you know, I think he was probably here before me most of the days, sorting out the registration, apart from organizing all the social things. Yeah, so that wouldn't have worked without the thing. But I don't mention the other people who are not here. So yeah, thank you. I'm switching to my other role again. We have ICGT next year. Most likely, and there's something seriously wrong with that, together with staff again, and that will take place in Twente. I think that is more or less confirmed.
That is confirmed, yes.
The date is not exactly confirmed. It likes to be around the same time.
Second or third week of July. It's a very safe bet.
Yeah. So, if you don't know Twente is sort of eastern Netherlands, close to the German border. So it's easy to reach for many people anyway, that are kind of in the more sort of Central European. But even I can go there by train. So it's still from here. It's manageable. I don't know if I want to train, but it's it may not. It may not if there are no strike. So it may not even take longer than by flying there.
I did come here by train.
So I think anyway, doesn't matter. So it will be sort of mid to end July, and really to figure out the details, but that's can assume for the time being. Right, so then, yeah, it was great to see you, and we have a little sort of informal steering committee meeting now, and I'll probably be at the bar in half an hour if you want to have a drink with me. But otherwise, yeah, enjoy the rest of the time here, and see you later or next time. Thanks.